Organic compounds. So early chemists divided things into organic compounds and inorganic compounds. And chemists use the word organic a little differently than they do like at the grocery store, or if you're online talking about health or something. Organic means that it comes from living things, right? Is everything that comes from a living thing natural? Well, yeah, it's natural, right? It's organic. Are all natural things safe and non-toxic? No, absolutely not. Rattlesnake venom is natural. Is that safe? Nope. Nothing is safe in excess. So organic comes from living things, and non-organic came from non-living things. Early in the science of chemistry, organic compounds were found to be much easier to decompose, easy to take apart, much easier than inorganic compounds, but it was harder to make organic compounds. It was much easier to synthesize inorganic compounds. Of course, now we figured out how to do all of those things. We can make or break any of them. So we can make organic compounds in the lab. You can also find them in nature. Your body's full of different organic compounds. Organic compounds are composed of carbon and hydrogen. So if it doesn't have carbon and hydrogen, it's not an organic compound. It may also have oxygen, nitrogen, phosphorus, sulfur. These are quite common in organic compounds, but other elements may be present as well. The key, though, is carbon. So here we have a structural formula and a space-filling model for the simplest organic molecule, which is methane. And one source of this is cows. Cow farts, to be specific. Here we have a carbon atom with single bonds to 4 hydrogens. What is very special about organic compounds is the carbon. Carbon forms almost exclusively covalent bonds. It really just doesn't do ionic stuff. And in this class, we can say it doesn't at all. Carbon always is going to form 4 covalent bonds. Those can be single, double, or triple bonds. It can make bonds with other carbon atoms or with different elements. So it can do all kinds of stuff. It really is a building block of life. You can end up with very long chains of carbon. You can form branches, branched, messy structures. You can make carbon in rings. All kinds of things are possible. Yeah?
Yeah, I forgot about that. You never answered my question about
I didn't answer your question about the graphene. We'll go there. You remind me. Can you remind me?
Yeah, during lab?
Just right at the end of lecture.
All right. You say carbons always have 4 bonds, is what you're saying?
Carbon always has 4 bonds. So here are some different organic compounds showing how carbon can bond. So we can have carbon atoms in a straight chain. We can have them branch. So here's 4 carbons, but instead of just being in a line, they're branching. We can have carbons in a circle. We can have double bonds. We can have triple bonds. Here's a double bond between carbon and an oxygen. But what's common in all of these things, you look at it, every single carbon has 4 bonds. This carbon has 2 bonds with the oxygen, 1 with this oxygen, and 1 with that. So carbon makes 4 bonds. So we can take all compounds, divide them into inorganic versus organic. Inorganic would include the acids, the molecular compounds that we've already learned about, and ionic compounds. Organic compounds can be broken down into hydrocarbons and functionalized hydrocarbons. So hydrocarbons with a twist. Hydrocarbons contain carbon and hydrogen. Hydrocarbon, hydrogen carbons.
I'm sorry, functional what?
Functional groups. Hydrocarbons are very useful. They burn very well and they give off a lot of energy. So oil, gasoline, liquid propane, natural gas, all of these things are hydrocarbons. We use them as fuels. Hydrocarbons can have all single bonds, in which case, as a group, they're called alkanes. They could have a double bond in them. If it has a double bond, then it's not an alkane. It would be an alkene. So we're changing this one letter here. A triple bond, and we're going to call it an alkyne. So we take the base name is determined by the number of carbons. And then we put a suffix that indicates, is it all single bonds? Is there a double bond? Is there a triple bond? So the suffix is going to be ane, ene, or ein. We're not even scratching the surface of organic nomenclature. We're looking at the surface. It gets much, much more complicated. But this is just an introduction. So you may recognize some of these prefixes: hex, hept, oct, non, dec. We used these for the hydrates and for the molecular compounds, but we had an A on the end of them, right? The ones that are different here are the first four. I'm pretty sure those have historical reasons for why they are what they are, but meth, eth, prop, and bute. And you got to remember those. I used to have trouble with that. This is how I remember it still. Mom eats pickled bananas.
Mom
Eats. For the small carboxylic acids, father ate pickled bananas. But we don't need to do that. Mom eats pickled bananas. You might be getting a brother or sister, right? Who would eat pickled bananas?
So
M for meth, E for eth, P for prop, and B for bute.
Is 10 going to be the highest, or just the highest we do?
Say that again?
10 deck.
We're not going to go higher than 10.
But it goes higher.
Yeah, it does go higher. Yeah. So these are the prefixes, and then you'd use one of these suffixes, ane, ene, or ein. So here are some common hydrocarbons. This top one. Come on, pointer. This is methane. So the ane tells me it's only single bonds. Meth tells me there's one carbon. It doesn't tell me how many hydrogens. You put in the number of carbons, and then you just fill in hydrogens so that all the carbons have 4 bonds. This is propane. Prop means 3. So there's 3 carbons. So there's 3 carbons in a row, and then we're just going to fill in with hydrogens around.
So ene is a double bond?
Ene means a double bond. So here's ethene. Eth means 2, and ene means there's at least one double bond. Here there's only one place the double bond can be, between the 2 carbons. Now there aren't as many hydrogens because each carbon can still have 4 bonds only, and because it has a double bond with the other carbon, it can only bond to 2 hydrogens instead of 3.
3 bonds.
And ethyne, the ein suffix means a triple bond. So here we have 2 carbons with a triple bond, and then you can only have 1 hydrogen on each end.
Is it possible to have a quadruple bond?
That's an excellent question. I was hoping somebody would ask that. Is it possible to have a quadruple bond?
It's the natural
Yeah.
order.
Not really, no. No.
There's just got to be something on the other way.
It's steric hindrance. It's geometrically highly improbable.
There's nothing on the opposite side.
It's like twisting yourself into a pretzel, or sticking your elbow in your ear, right? You just can't. It's not possible. You'd have to break your arm or something, right? It's just not going to happen. Here's butane and pentane. Pentane means 5. Here the pentane has the 5 carbons just in a row, and so that's why it has the N in front. N stands for normal, It's just straight chain. So you could have 5 carbons that were in a branched configuration. We're not going to go there.
I was like, when I was going to math, it has like n number of endings.
Yeah, N is just for normal, means a straight chain. So N-butane means that those are in a straight line.
Isn't there something that you do to tell where the double or triple bond is?
Yes. There's a whole system of telling where the double bond is. We gave you 2 examples there where there were only 2 carbons. So the double bond has to be between those 2 carbons. But if I had butene, if I had a double bond in here, would it be on the end or in the middle? It's 2 different places. Well, then you have to have something in the name that tells you. And so you'll learn that in organic chemistry.
Oh, we don't do that.
We don't do that here. Functional groups. Function, right? It's a function. It does something. Functional group changes the functionality or changes the chemical properties of the compound. We could argue that a double bond or a triple bond is a functional group because that does change the functionality of the substance. So we can put these organic compounds into different groups based on what their functional groups are. Methanol and isopropanol are both members of the alcohol family. And you don't need to know how to name these, but this OL at the end is because they're both alcohols. When we look at their formulas, they both have OH. And that's what makes it an alcohol.
So we're not learning that either? Alcohol?
No, we're going to learn to identify that that's an alcohol, but we're not going to learn how to name it.
What's iso? Is
That's a good question. What's iso? So this thing has 2 different names. It could be called 2-propanol or isopropanol. It has 3 carbons. That's why it's prop. And they're in a line, although it looks like it's curved here. And the functional group is on the middle carbon.
So
That's what the iso means. Because if you put the functional group on the end carbon, then you have just propanol, and that has slightly different properties than isopropanol.
That's crazy. Same thing, just a different spot.
Right. So these are isomers. They contain the same number of atoms of each element, but they're connected differently, and that can have huge effects on the properties. So they would have the same molecular formula, but their structural formulas are different. And so in the organic compounds, you could, in organic chemistry, you can have a single molecular formula, and you might have 5 or 6 different compounds with the same molecular formula. And if you look at empirical formulas, it's even crazier. So these are the functional groups. So I want you to be able to recognize alcohols and carboxylic acids and amines. You might have to do something else on homework or a worksheet or something, but I wouldn't ask you to do anything else on an exam.
Just these 3?
Just those 3. So an alcohol has this OH group. The OH is bonded to carbon, and the carbon's just got other carbons and hydrogens on it. In a carboxylic acid, this also has an OH group on it, but now the carbon there that the OH is on is double bonded to an oxygen. A lot of acids are carboxylic acids. They are organic acids. Acetic acid is an example of that. That's what's in vinegar. That's actually an organic compound. Amines, you recognize those because they have nitrogen in them. So this is essentially a variation of ammonia. Ammonia, amine. It's nitrogen. In ammonia, this would be a hydrogen. In amines, there's something else on there.
So what makes it carboxylic acid?
A carboxylic acid is going to have this double bond with an oxygen and an OH group on the same carbon. On the same carbon. Because up here, the double bond with the oxygen, aldehydes and ketones also have that, but it's only a carboxylic acid if those are on the same carbon.
And the amines is the NH?
Amines is if it has nitrogen in it.
Oh, just nitrogen, not the H's?
Well, it would be, there would be H's.
Okay.
But, we're keeping things really simple. And so if it's got nitrogen in it, call it an amine. Okay, so draw the structural formula for nonane. Well, how many carbons in nonane? 9, right? Because nona means 9. This is the sort of math we deal with in OChem. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a lot of counting, and usually you don't have to count past 10. Just a lot of counting. So there's my 9 carbons. I'm going to put them in a line because we're only doing straight chain hydrocarbons. Then we have to put hydrogens on there. So the hydrogens, we're going to add hydrogens so that all of these carbons have 4 bonds. So top and bottom, right and left would give us 4. So we can just kind of make a little grid out of this. If I put bonds like this, then each of these carbons is going to have 4 bonds, right? And so then I'll have to slap a hydrogen on the end of each of these.
So the ane means that it's only a single bond all the way.
Yep. Nonane means there's only single bonds. Oops, need one down there. Tedious, very, very tedious.
I was watching some of the OChem students in the Latin tutorial center.
Yeah.
Doing all that hexagon
Oh yeah,
stuff.
all kinds of crazy stuff.
Holy crap.
What if we made this into no 9 instead?
Is that YN or E?
It's a YNE,
Triple bonds.
a triple bond. Now, we're not learning how to indicate where the triple bond goes. So if I asked you to draw a structural formula for no 9, you could put it anywhere and I would count it correct. So, I don't know, let's put it on the end. So there's 3 bonds there. I need to adjust the numbers of hydrogens though, right? Because carbons have 4 bonds. And if I look at this carbon right now, it has 1, 2, 3, 4, 5, 6. So I need to get rid of some. So I need to get rid of this hydrogen, and I need to get rid of that hydrogen, so that that carbon has 4 bonds. And the carbon on the other end of the triple bond also has an issue with too many, and so I'm going to get rid of those so that it only has 4 bonds. Okay, carbon always has 4 bonds. If I gave you a picture like this, you should be able to come up with this very general name.
So it'll only have one where it's bonding 3 to a triple bond to a carbon, and then 1 to a hydrogen.
Are you asking if there will only be 1 triple bond?
Yeah.
There could be more than 1 triple bond. It could have 3 triple bonds.
But it's still an ane.
It would still be a no 9, but each of those is going to have a specialized name that we're not learning about.
Oh, there's ISO.
Yeah.
So where the bond is in there, does it make a big difference on the properties of it?
It does. Yeah. So with the triple bond on the end versus the triple bond in the middle somewhere, it's going to have different chemical properties. And one of the really cool things about organic chemistry is synthetic organic chemistry, where you're trying to make a compound in the lab. One of my sons is doing some research on fruit fly pheromones to use as attractants in traps. And so you need to make this organic compound. Well, you can't just go order it off the internet because nobody makes it, right? So you have to figure out how to make it. And so there's all of these different possible chemical reactions, and it's like this big puzzle to figure out, well, if I do this in this order, the bromine goes on this one, but if I do it in this other order, the bromine goes over there, and how can I get it to come out to be what I want? And if you like that sort of thing, it can be really, really fascinating, or it could make you bonkers.
I want to do materials science engineering, so maybe might have probably not as much as chemical, but
Not as much, no, but yeah, you'll probably need OChem. And then we should be able to answer questions like this. Now, this one would not show up on an exam because it's not one. So I'm going to change it. So, to which family does that compound belong? I'm only asking you to know 3. Is it an alcohol, carboxylic acid, or an amine? It's a carboxylic acid. If it didn't have this double bond oxygen, it would be an alcohol. But because these are there, it's carboxylic acid.